Section 6.1, Exponential Functions and their Graphs. In this section, we will learn to identify exponential functions, graph exponential functions and determine their domain and range, whether the function is increasing or decreasing, any intercepts, and asymptotes of the graph. We'll learn how to graph transformations of exponential functions. We'll talk about exponential growth and decay, and we'll also compare linear and exponential growth. The most basic form of an exponential function is given by f of x is equal to b to the x power, where b and x are real numbers, b is greater than 0 and not equal to 1. We call b the base of the function, and the domain of f of x equals b to the x is the set of all real numbers. Which of these functions are exponential? Alright, f of x is equal to 25 to the negative x. Well, it appears that we have a base raised to a variable power. 25 to the negative x, this is exponential. And if we wanted to, we could use properties of exponents to rewrite this. So notice 25 to the negative x, that's the same as 25 to the negative 1 to the x power, which is 1/25 to the x power. And so if we look at it in that way, it's definitely an exponential function, because we have a base of 1/25 raised to the exponential power. Let's look at the second example. Here we have p of t is equal to negative, or maybe I should say the opposite of 25 to the t. So we have 25 raised to the t power, and then that's being multiplied by negative 1. Now be careful. Okay, so this is exponential. But if we had negative 25 to the t power, that would not be exponential. We would say that this is not exponential because the base is negative, and we don't want the base to be negative. We want the base to be positive, but not equal to 1. And what we have here is the base is 25, it's being raised to the t power, and then being multiplied by negative 1. Third example, we have f of x is equal to 4/7 to the x. Well, we have a base to a power, 4/7, and 4/7 is greater than 0, so this is exponential. And we have finally p of t is equal to t to the 2/3 power. So here, notice we do not have a variable exponent. And t is not a constant. See, this is what's called a power function. Alright, so in general what we're looking for is the base to be a number, a constant, and the exponent to be variable. Alright, so let's look more in depth at a particular function. Let's construct the graph of f of x is equal to 3 to the x power. I will start this by using a table of values, and I will choose as my inputs negative 3 to 3 by 1s. And I'll start with maybe the easier values. If x is 0, 3 to the 0 is 1. If x is 1, 3 to the first is 3. If x is 2, 3 to the second is 9. And if x is 3, 3 to the third is 27. Now what if x is negative 1? Well, 3 to the negative first power is 1/3. 3 to the negative second power is 1/9. and 3 to the negative third power is 1/27th. All right, so we have these points. I'm going to use just a scale of ones on each axis. So 1, 2, 3, 4. Let's see, 1, 2, 3, 4. I'll mark this as 5, 6, 7, 8, 9. There's 10. All right, plotting the points. Negative 3, 1/27th. 1/27th is pretty close to 0. So we get a point there. Negative 2, 1/9, up a little higher. Negative 1, 1/3, a little higher. 0, 1, 1, 3, 2, 9, and 3/27th is 3, 27 is off of our grid. All right, so I'm going to connect these points with a smooth curve, or do the best I can at that. And so here we have an exponential function. Notice how I drew that curve as I was moving to the left, or I should say coming from the left. It's very close to the x-axis, but actually will not touch it. All right, so we have what's called a horizontal asymptote. All right, so we have a domain, negative infinity to infinity, all real numbers. Our range, we get very close to 0, but don't cross it. So range is 0, and we can go onward all the way to infinity. We have a horizontal asymptote at y equals 0. And that's that dotted orange line that I drew. All right, what if we were asked to graph f of x is 1/3 to the x? Well, I'm going to start off the same. If x is 0, then I would have 1/3 to the 0 power, and any non-zero number to the 0 power is 1. If x is 1, I'd have 1/3 to the first, which is 1/3. If x is 2, I'd have 1/3 to the second, which is 1/3 times 1/3, 1/9. And if x is 3, I'd have 1/3 cubed, 1/27th. Now hopefully you're saying to yourself, well, is there a pattern here? And of course the answer is yes, there is. If x is negative 1, I'd have 1/3 to the negative first power. Well, using our understanding of negative exponents, that's the same as the reciprocal of 1/3, which is 3, to the first power, which is 3. And following a similar pattern, we would have 27 and 9, respectively, for when x is negative 3 and negative 2. Now, if we plot these points, I'm going to use the same scale. Let's see, we have negative 3, 27, that's off of our scale. Negative 2, 9. Negative 1, 3. 0, 1. 1, 1/3. 2, 1/9. 3, 1/27th. Now that looks pretty much like the graph we drew in the previous slide. It's just been flipped horizontally. Again, we have the horizontal asymptote at y equals 0. So again, we have the domain, negative infinity to infinity, range, 0 to infinity, and horizontal asymptote at y equals 0. Now, of course, I look at this graph and I see this as a transformation of the graph we had earlier. So notice that 1/3 to the x is the same thing as, is equivalent to 3 to the negative x. And so if you think of what we talked about in Chapter 3 with transformations, if I replace x with a negative x, that's a horizontal flip. And we can see that from in this graph. All right, let's compare and contrast the graphs of f of x is 3 to the x, f of x is 5 to the x, and f of x is 10 to the x. And I'll use a calculator to do this. All right, so in my y equals screen, there we have 3 to the x, y2 is 5 to the x, and y3 is 10 to the x. And let's graph. Let me check my window. Let me go negative 10 to 10 on each axis, and a scale of 1s. Alright, and I see 3 graphs. Let me change the window so we get a better picture. How about we just go from, say, negative 3 to 3 on the x-axis, and how about negative 1 to 10 on the y-axis? Alright, and I'm going to grab this picture and bring it onto the... Alright, so here's that picture. Now, this one was the first graphed, and this was, so that's 3 to the x. In the middle, there's 5 to the x. And toward the left, there's 10 to the x. So compare them. What's the same? All right, well, they are all increasing as we move from left to right. They all appear to have the horizontal asymptote. They all appear to have the same y-intercept at 0, 1. And they have the same basic shape. Now, let's contrast them. How are they different? And the difference in the graphs is really on how they increase. All right, so notice that 3 to the x is increasing the slowest, especially for positive values of x. It's tougher to say what's happening over here on the left from this graph, right? It's tough to say what's happening in here. But let's consider when x is positive. When x is positive, notice that 10 to the x increases most rapidly. All right, 10 to the x is increasing the fastest. Then 5 to the x, and then 3 to the x. Well, what about what's happening to the left? What about when x is less than 0? Let's look at another picture. So let's go back to our graph, and let's focus in on what's happening between, say, negative 2 and 0, and on the x, and just between 0 and 1 on the y. Now let's look at that graph. So now let me bring that picture onto the slide. So the first graph that was drawn is the one on top, and the second was the one in the middle. That's the 5 to the x, and the third one was the 10 to the x. So notice, and they all have the same y-intercept at 0, 1, but notice that when x is less than 0, the graphs have sort of switched positions, right? When x is less than 0, we see that 3 to the x is greater. Now, we usually are most concerned with what happens eventually, what happens to the rate of increase for positive values of x. So I'm more concerned with this part, that when we have positive x values, the larger base will increase most rapidly. Now, what if we had the graphs of 1/3 to the x, 1/5 to the x, and 1/10 to the x? All right, so again, let's look at the calculator. All right, go back to my y equals screen, and we have 1/3 to the x. Oops, let's try that again. We have 1/5 to the x. And we have 1/10 to the x. All right, and let me go back to the window -3 to 3. And let's go -1 to 10 on the y's. All right, in the graph, there's the first function, second, third. All right, let me grab that picture and put it. All right, so we have 1/3 to the x, 1/5 to the x, and 1/10 to the x. All right, so notice that they are all decreasing. They have the horizontal asymptote. At y equals 0, they have the same y-intercept at 0, 1. But now look at those rates of decrease. Look at how steep they are. And so notice that the 1/10 to the x has the steepest decline. All right, so notice f of x equals 1/10 to the x is the steepest decline. But otherwise, they're pretty much the same graph. All right, so let's put some of those and let's put that information together. All right, so some generalizations. For the function f of x equals b to the x, where b is greater than 0, not equal to 1, the domain is a set of real numbers, -infinity to infinity. The range is the positive real numbers, 0 to infinity. The y-intercept is 0, 1. The x-axis will be the horizontal intercept, is a horizontal asymptote. Sorry about that. The function is 1 to 1. We can see that by applying the horizontal line test. If the base is greater than 1, the function is increasing, and the larger value of b, the steeper the increase. If the base is between 0 and 1, the function is decreasing, and smaller values of b produce steeper decrease. All right, so let's find an example. Let's look at this example. We want to find the exponential function whose graph is shown, and we're given a couple of points here. We see the point 0, 1, and we see the point 2, 10.24. So exponential function, I'm going to assume at this point that we're looking for something of the form y equals b to the x. So we really only need to figure out the base. Notice it goes through 0, 1. So we expect it's going to be of the form y equals b to the x. All right, so let's figure out the b. So let's use this point, 2, 10.24. Well, that means that 10.24 should be equal to b to the second power. Applying square roots, b would equal only the positive square root of 10.24. We can't have a negative value for b in this situation, or we don't have an exponential function. So even though we really should have a plus or minus, in this context we only can accept the positive root. Going to our calculator, the square root of 10.24 is 3.2. b is equal to 3.2. And so then our function should be y equals 3.2 to the x. Apply transformations to graph the function. Determine the horizontal asymptote and the y-intercept of the function. We're asked to do this with 3 to the x plus 2 plus 4. So I think of this as a transformation. My base function is 3 to the x, which we know how to graph now. So if I wanted to come up with a few points, maybe I could say, okay, let's go with x and 3 to the x. And so I'm just going to go with a few of the points that we had, about -1, 0, 1, and 2. And so that was 1/3, 1, 3, and 9. All right, now let's think about this. Using the transformations, let's see, x plus 2. I need to shift left 2. So if I'm going to shift left 2, then I'm going to subtract 2 from all of these. That would give me a -3, a -2, a -1, and a 0. Plus 4. That's a shift up 4. So I'm going to add 4 to all of these. Let's do the easy ones first. 5, 7, 13. 1/3 plus 4 is 4 and 1/3. I'll think of a mixed number here. Now, also, it says horizontal asymptote. Where's the horizontal asymptote? Well, the regular horizontal asymptote is the x-axis, right? Y equals 0, but it's also being shifted up 4. So the horizontal asymptote is going to be at y equals 4. All right, so let me go ahead and draw that in. And now let's plot some points. I have -3, 4, and 1/3. I have -2, 5. I have -1, 7, and 0, 13. So let's see, -3. Let me just use a standard scale. All right. 1, 2, 3, 4, and 1/3. That's going to be about here. -2, 5. -1, 7. And 0, 13, 10, 11, 12, let's say 0, 13 is about here. Taking into account the horizontal asymptote, I get a graph that looks roughly like this. And I do have it asks for the y-intercept. The y-intercept is 0, 13, when x is 0. All right, f of x is equal to the opposite of 2 to the x minus 3. All right, now we didn't graph 2 to the x, we graphed 3 to the x, but 2 to the x isn't much more difficult. Let's look at the base, right? My base function is 2 to the x. All right, so let's plot a few points, or get a few points from that. X versus 2 to the x, and I'll just use a similar few points. That would give me 1/2, 1, 2, and 4. All right, now let's look at the x. There's no transformation on the x, so I'm not going to shift left or right any. Okay, but we do have this negative. All right, so what does the negative do? The negative changes the signs on the output. Right? It's multiplying by a -1. It's giving me a flip. So I'm going to take all these and multiply by -1. Right? So the opposite of 2 to the x would give me a -1/2, a -1, a -2, and a -4. And now I've got to subtract 3. All right, so that's a shift down 3. All right, so -1/2 minus 3, that's -3.5, -4, -5, -7. All right, so some points on the curve: -1, -3.5, 0, -4, 1, -5, 2, -7. Horizontal asymptote? Well, the horizontal asymptote has been shifted down 3 as well. Y equals -3. Right, so let me draw in my dotted line. Let's plot some points. -1, -3.5. 0, -4. 1, -5. 2, -7. We see the basic shape, so kind of filling in the rest. All right, and you might say, well, wait a second, the base was 2, why isn't it increasing? Why do we get a decreasing function? Well, since we had to flip, all right, that's a vertical flip, we should expect a decreasing function now. All right, so there's the graph of the function, and what is the y-intercept? Y-intercept, when x is 0, 0, -4. All right, one more example of this. Here we have f of x is 6 to the -x plus 2. Well, again, I'm going to create my base. My base is 6 to the x. And I'll just do a few points on this. X versus 6 to the x. Let's see, if x is -1, 0, and 1, 6 to the x would be 1/6, 1, and 6. If I went to x equals 2, then I'd have to have 36, and that's not going to show up well on a standard scale. All right, but wait a second. I have a -x. So what does a -x do? All right, that's a horizontal flip. All right, that changes the sign. So let me change all these signs. +1, 0, -1. And let's see, no shifts, but now I'm going to add, no horizontal shifts, but now I'm going to add 2. All right, so let's shift these up 2. So 2 and 1/6, 3, and 8. Where's my horizontal asymptote? Horizontal asymptote has been shifted up 2, so that would be at y equals 2. Now 6 to the x is an increasing function, but since it's now 6 to the -x, we have a horizontal flip. We should be expecting a decreasing function. Well, so let's see, let's plot the points. I have 1, 2, and 1/6. I have 0, 3, and I have negative 1, 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 8. And filling in the rest. We do see a decreasing function. The y-intercept is 0, 3. All right, one more transformations. F of x is 4 times 3 to the x. Let's start with our base, which is 3 to the x. So x versus 3 to the x. Negative 1, 0, 1, and 2. Let's see, that would give me 1/3, 1, 3, and 9. Now let's see, what's happening here? No shifts left or right, no flips. All we have is this 4. Well, that's a scale factor. So I'm going to multiply all of these by 4. So 1/3 times 4, that's 4/3. 4, 12, and 36. So I have negative 1, 4/3. I have 0, 4. I have 1, 12, and 2, 36. Where's my horizontal asymptote? Well, it hasn't been shifted, right? There's been no shifts up or down, so the horizontal asymptote is still on the x-axis, y equals 0. We have the y-intercept, 0, 4. And let's plot points. Negative 1, 4/3, that's negative 1, 1 and 1/3. 0, 4. 1, 12. 11, 12 would be up here. And 236 would be way off our grid. But it still has to have the same basic shape, so we know it's going to have this horizontal asymptote and then rapid increase. And so there's the graph of the function. For each function, find the vertical intercept and determine whether the function is increasing or decreasing. All right, finding the vertical intercept is relatively easy, right? We evaluate the function at 0. So let's see, f of 0 would be 3 times 5.1 to the 0. Following the order of operations, that would be 3 times 5.1 to the 0 is 1, and 3 times 1 is 3. So f of 0 is 3. There's the vertical intercept. Now, is the function increasing or decreasing? Well, let's focus on the base. My base is greater than 1, so that leads me to believe it's increasing. My exponent is just a plain old x. There's no flip there. My scale factor is positive. There's no flip there. All right, so increasing. Let's look at the second example. P of t is the opposite of 8/9 to the t. F of 0, I should say P of 0, is the opposite of 8/9 to the 0. 8/9 to the 0 is 1. So P of 0 is negative 1. The vertical intercept is 0, negative 1. All right, now let's look at our base. Is this function increasing or decreasing? Our base is between 0 and 1, so that leads us to think it's decreasing. However, we have this negative. We have a vertical flip. So we have a function that's decreasing, but wait, we flipped it. All right, so if we had a function that was decreasing, I'm just drawing a rough exponential decreasing function, and we give it a vertical flip, we get this graph that I drew dotted. We get an increasing function. So due to the vertical flip, we get an increasing function. All right, let's look at our third example. G of x is 2.3 times 3/7 to the negative x. G of 0 would be 2.3 by 3/7 to the opposite of 0. Well, the opposite of 0 is 0. 3/7 to the 0 is 1, so I have 2.3 times 1, and that's 2.3. All right, now let's determine if it's increasing or decreasing. Our base is between 0 and 1. So that leads us to believe it's decreasing. But we have a horizontal flip. All right, so again, if we have a decreasing function, all right, there's my rough decreasing exponential function, but we give it a horizontal flip, then I get this graph that I'm drawing dotted. And so we get an increasing function. Well, we also have this 2.3. Does that change things? Well, the 2.3 does not give us a vertical flip, right, since it's positive. So we would stick with increasing. Well, now let's talk about exponential growth and decay. Consider the function p of t equals 5 times 4 to the t, which models a population in terms of the number of days. What is the initial population? All right, when we talk about initial, that means when the time is 0. So p of 0 would be 5 times 4 to the 0, which is 5 times 1, which is 5. So the initial population is 5. How does the population consistently change each subsequent day? Well, let's create a table of values to look at this. So here we have t versus p of t, and let's start at 0. At 0 we have 5. After 1 day, we would have 5 times 4 to the first power. That's 5 times 4, which is 20. And after 2 days, we would have 5 times 16, right? 4 to the second. 5 times 4 to the second, that's 5 times 16, that's 80. After 3 days, we would have 5 times 4 to the third. 4 to the third is 64. And that's 320. Do we want to take it another step? It might be a little bit more difficult. Do you see a pattern here? Now, we talked about linear patterns in a previous chapter, but a linear pattern doesn't work here. Notice we have, an increase of 15, and then an increase of, 60. So this is not linear. What's going on here? Notice 5 times 4 is 20. 20 times 4 is 80. 80 times 4 is 320. 4 days, the exponent increases by 1, so we're multiplying by another factor of 4, and we'd have 1,280, and so on. So each subsequent day, multiplying the population by 4. We say that this population function has a growth factor of 4. So, the basic exponential growth and decay function is given by p of t is p0 or p naught, right? We sometimes say p0 or p naught. P of t is p naught b to the t. where t is time, representing time. P naught represents the initial amount or value of p at time 0. And as long as it's positive. B represents the growth factor if b is greater than 1, or the decay factor if b is between 0 and 1. Okay, so p sub 0, that's an initial value, and b can be thought of as the growth or decay factor depending on its value. So here's an example. As of 2010, Facebook was considered the world's largest social network. The number of Facebook active users in millions can be modeled by the function p of t is 1.53 by 2.82 to the t, where t is the number of years after 2004. Is this function increasing or decreasing? Explain. Well, if I look at the base, 2.82, that's greater than 1. And there's no horizontal or vertical flip. So this is an increasing function. Base is greater than 1, and we have no flips. Identify the growth factor. The growth factor is 2.82. What does that mean? Each year, right, if t is the number of years, each year the number of users increases by a factor. All right, so that's multiplying, not adding, multiplying, of 2.82. Approximate the number of active Facebook users in 2009. Now, t is the number of years after 2004, so 2009 would mean t equals 5. So then p of 5 would be 1.53 by 2.82 to the 5th power. We're going to use a calculator for this. Uh, 272.9. Let's take it to 2 decimal places. 272.86. All right, so in 2009, there were approximately 273 million active Facebook users. The following table displays values for an exponential function. Determine whether the function represents exponential growth or decay. Find the growth or decay factor and complete the table. Alright, so if it's representing an exponential function, but it doesn't go through 0, 1, it goes through 0, 2, then notice my P0 is 2. Alright, my initial value is 2. So I can start by saying, well, P of t is 2 times b to the t. Now, it appears to be decreasing. So this is exponential decay. Which means we are expecting our b value to be between 0 and 1. So let's remember that. So now we choose another point. Well, I'm going to use the second point, 1, comma, 0.8. So then, when t is 1, I should say x, right? This function was called p of x. When x is 1, p of x is 0.8. So then I have 0.8 is equal to 2 times b to the first power. Well, b to the first power is b, and dividing through by 2, b is 0.4. So then my function then is p of x is 2 times 0.4 to the x. And now I'll use a calculator to calculate the remaining values. When x is 2, I'd have 2 by 0.4 to the second power, which is 0.32. And when x is 4, second enter, and change that 2 to a 4, 0.0512. All right, that completes the table. And we can check the other values if we want. Let's just make sure that it works for x equals 3 at least. We get 0.128, which matches what's already in the table. Determine a model for the following statements. An initial population of 15 doubles every week. If I let t represent the time in weeks, and we see that an initial population of 15. All right, so p of t then would be the initial population, p0, 15, and then b to the t. Now the base is, what's the base? Well, it doubles every week. So that means the growth factor is 2. Doubling is multiplying by 2. So we'd have 15 times 2 to the t power. But what if we change it up and say now the initial population is doubling every 5 weeks? Well, if we still let t represent the time in weeks, then the growth factor is not 2, because that's how it changes every change in t. T is in weeks. It's not doubling every week, so it can't be the same model. But we can start off similar. We can start off by saying p of t is equal to 15 times b to the t. Now we know that every 5 weeks the population doubles. So now we create the point when t is 5. After 5 weeks the population doubles. So we would have the point 5, comma, 30. After 5 weeks, the initial population of 15 doubled to 30. So now we have 30 is 15 times b to the 5th power. Dividing through by 15, we have 2 is equal to b to the 5th. And we can solve this by raising both sides to the 1/5 power. And using the calculator, 2 raised to the 1/5 power is let's take it to 4 places, 1.1487. So then our model would be p of t is equal to 15 by 1.1487 to the t. It is still growing, right? Notice that the base is greater than 1, so we do get exponential growth here. An initial population of 3,000 increases by 12% every week. Well, again, let t represent the time in weeks. Now, if we increase by 12%, If you increase a number by 12%, what are you multiplying by? So let's think about this. If I take a number and I increase it by 12%, I don't just add 0.12, I increase it by 0.12x. Now this original x was a 1x, so 1x plus 0.12x, that's 1.12x. So if you increase a number by 12%, it's the same as multiplying by 1.12. So P of t is 3,000 times 1.12 to the t. Now what if we have a population that decreases by 12% every week? Well, we could think of a similar idea. We have x, and we're going to decrease it by 12% of x. Again, we started off with a 1x, and 1 minus 0.12 is 0.88. So if you decrease a number by 12%, that's the same as multiplying the number by 0.88. One way to sort of think about this is if you remove 12%, 88% remains. So then P of t is 3,000 by 0.88 to the t. And notice that this is a decreasing function. It's between the base is between 0 and 1. And so often, if we are given a percent increase or decrease, we can often think that the base is equal to 1 plus the rate for an increase. The base is 1 minus the rate for a decrease. And of course, that's only if those rates are given as percentages. An initial population of 3,000 decreases by 26% every 3 weeks. Alright, so this one's a little tougher. If we let t represent the time in weeks, we know we have P of t is 3,000 b to the t. We have to figure out the base. It decreases by 76% every 3 weeks. So 74% remains after 3 weeks, right? 74% remains after 3 weeks. So that gives me the point. Let's see, what's 74% of 3,000? 2,220. So after 3 weeks, 2,220 remain. Substituting, we have 2,220 is equal to 3,000 b to the third. We divide through by the 3,000. And that better come back with 0.74. .74 is b cubed. Raise both sides to the 1/3 power. Take that to 4 places, that's 0.9045. So b is approximately 0.9045. So our function then would be P of t is 3,000 by 0.9045 to the t. Again, a decreasing or exponential example of exponential decay. Let v of t equal 10,000 times 0.925 to the t represent the value of a motorcycle in dollars after t years. Alright, what is the initial value of the motorcycle? I can see that directly from the function, Or if I let t equal 0, the initial value is 10,000. So $10,000. Is this value increasing or decreasing? Well, the base is 0.925. Decreasing. The base is between 0 and 1. Identify the growth and decay factor. 0.925 is the decay factor. Alright, so identify the percent increase or decrease per year. Alright, so we know it's a percent decrease. Now 0.925, if we think of the base as being 1 minus r, solving for r, we find that r is equal to 0.075. So what is that telling us? That's a 7.5% decrease per year. What eventually happens to the value of the motorcycle? Well, this is basically an exponential function. It's decreasing, and so if we thought about it graphically, we get a graph that does, there's 10,000, we get a graph that does this. What happens to the value of the motorcycle? The value of the motorcycle eventually approaches 0. Dollars. Suppose, for an experiment, the initial population of fruit flies is 200 and that the population grows to 2,000 after 15 days. Determine a linear function that models this situation. Alright, so linear, to find a linear function, we need to figure out a slope and an intercept. Alright, so let's see. Let's come up with some points. The initial population of fruit flies is 200. So we have 0, 200. The population grows to 2,000 after 15 days. So 15, 2,000. Alright, so if we're going to let t represent the time in days, our slope then would be 2,000 minus 200 over 15 minus 0. So that's 1,800 over 15, which is 120. And since we have the point 0, 200, we'll call this L of t, our linear model for t. Our linear model of the population is going to be 120t plus 200. Alright, so the population started at 200 and was increasing by 120 per day. Now, determine an exponential function. Again, if we let t represent the time in days, we have 0 to 100, so I'll go with e of t. My exponential model would be then 200 times b to the t. Now, using the other point, 15, 2,000, I would have 2,000 equals 200 b to the 15th power. Divide through by 200. And that would give me 10 is equal to b to the 15th. I'll raise both sides to the 1/15th power. And we have b is 1.1659. So then e of t would be 200 by 1.1659 to the t. All right, so there's a linear function and an exponential function that models this data. Now let's see how they compare. Let's graph both functions. We're going to compare the functions between days 0 and 15 and after day 15. All right, y equals, let's clear out the old stuff. We have 120x plus 200. That's my linear function. My exponential function, 200 by 1.1659 to the x. Just to clearly identify the two, I'm going to draw y2 in bold by moving to the left of the y2 and hitting enter one time. All right, let's think of a scale to use. Window. Well, we know we need to go from 0 to 15. We need to at least see up to 15 days. So let's go to 20 days. I'll use a scale of ones. And on the populations, well, we know the minimum population, either of those models, was 200. And we know we get to 2,000 after 15 days. So let's go up to, say, 3,000. And I'll use the scale of hundreds on the y-axis. Alright, let me grab the picture and put it on the slide. Alright, so here we have our linear function and our exponential function. So notice, between days 0 and 15, so when t is between 0 and 15, L of t, the linear function, is greater than the exponential function. However, for t greater than 15, the exponential function is greater than the linear function. And they will never cross again. That exponential function, remember, if you remember how the graph of exponential functions look, that exponential function is going to increase very rapidly, whereas the linear function is going to keep on, right, steadily increasing very slowly as compared to the exponential function. All right, so eventually, if we compare increasing linear and exponential functions, eventually an exponential function will be greater than a linear function. Eventually. All right, if we have two functions that are both increasing, one linear, one exponential, eventually the exponential function will overtake the linear function. All right, that completes the presentation for this section.